In this class, we are going to discuss about parity operator and the parity of harmonic oscillator wave function. So let's first see how to define the parity operator. The parity operator is defined by its action on the Ketz R. By its action on the Ketz R of position space. So suppose we denote this parity operator by this symbol pi. Then this parity operator acting on this position space is basically gives you minus of R, or if it acts on the bracket on the bra, this is defined as minus of R, such that parity operator acting on the wave function psi of R, which basically gives you the inversion of this wave function psi of minus R. It is a Hermitian operator, and to show that, let's consider the arbitrary states phi and psi. So two arbitrary states we are going to consider. Let me say phi and this parity operator acting on psi. Now this can be expanded by inserting an identity operator. So we can write it as integral minus infinity to plus infinity. Let's consider the one-dimensional case for simplicity. Then dx phi, the parity operator. Then I'm going to introduce the identity operator in position space. So that is x bra x. Then we have psi. Now by the definition, this pi acting on x should give you minus of x. So this can be defined as integral minus infinity to plus infinity dx integral phi, then this will be minus x, then we have x psi. So this can be written as integral minus infinity to plus infinity dx. Then let me reverse the order. Then I can write it as minus x phi, the complex conjugate. Then this is the projection of psi to the position space. So this is psi of x. This is integral minus infinity to plus infinity dx. Then this is phi star of minus x, because it gives you the projection of this ket phi to minus x ket minus x. So this is into psi of x. Now we change the variables by taking, let's take a new variable x prime, which is equal to minus of x. Then this integral minus infinity to plus infinity dx phi star of minus x psi of x will become integral minus infinity to plus infinity dx prime phi star of x prime psi of minus x prime. So we have changed minus x to x prime to a new set of variables. This will become integral minus infinity to plus infinity dx prime. Now phi star of x prime can be written as phi in the new variable x prime, then psi of minus x prime is given by minus x prime, then get psi. Okay, that is equal to integral minus infinity to plus infinity dx prime phi x prime, and then let me reverse this order, psi minus x prime all star. So this is same as integral minus infinity to plus infinity dx prime phi x prime. Then this last term can be written as psi, then the parity operator acting on x prime ket, then the complex conjugate, right? Because when parity acts on this x prime, that will give you minus of x prime. That is the definition of the parity operator. So this is integral minus infinity to plus infinity dx prime phi of x prime. Then you can write it as, this last thing can be written as x prime. Let's again reverse this order, or here, let's consider the complex conjugate. So this will be the parity operator, the adjoint of the parity operator psi. So it gives you that this is phi, the adjoint of the parity operator psi. So what was on left side? Basically it was phi. So this was our starting point. Left side is phi pi psi, and right hand side is phi pi star psi, and this will give us the parity operator pi is equal to its adjoint, hence it is a Hermitian operator. So parity operator is a Hermitian operator. So now let's consider the inner product of two arbitrary state vectors phi and psi. So let's say bra phi pi square. So we are considering the squaring of parity operator. So this is can be written as integral minus infinity to plus infinity, like what we did with the previous case. We are going to introduce an identity operator in position representation. So this is phi pi square x then psi equal to integral minus infinity to plus infinity dx phi pi. When pi adds once, you will get minus of x here, then x psi. This is equal to integral minus infinity to plus infinity dx phi. Then when pi adds once more, you will get minus of minus x, so that will give x. Then we have x psi. So this is because this will give by definition x. Okay, so this is, we have phi, then you have an identity operator, then psi, right? So it tells you that the action of the square of the parity operator is equivalent to an identity operator, or you can write this is same as the inverse of the operator, because pi inverse will basically gives you this identity operator. And we had already seen that this parity operator is equal to its adjoint in the previous derivation. So you can write it pi inverse or pi dagger equal to pi equal to the identity operator, or you can write from these two expressions, you can write pi dagger equal to pi inverse. So hence these are unitary operator too. So we have seen that parity operator is a unitary operator and it is also a Hermitian operator. Now since the square, because of this property, the parity operator acting twice gives us the identity element, then we can write an eigenvalue equation of the form, let's say P acting on psi of r equal to, let's say, some eigenvalue pi, then psi of r. So this is the operator, parity operator, and this pi without any hat gives you the eigenvalue of that corresponding operator. So we have written an eigenvalue equation for the parity operator, but we know that when this parity operator acting on this psi of r, by definition this will give us psi of minus r. Okay, and this can be written as the eigenvalue times psi of r. Now since pi square equal to I, the eigenvalue of pi square operator can be plus 1 or minus 1. So this can be either plus 1 or minus 1, because the square of this one will give you the identity operator 1. So the corresponding wave functions, let's say when you have an eigenvalue of plus 1, let's denote the corresponding wave function as psi plus, and when you have an eigenvalue of minus 1, let's denote the corresponding wave function as psi minus. Then for plus 1 eigenvalue, you can write that expression, this expression, as psi plus of minus r is equal to psi plus of r, and this is called an even wave function or an even wave function. If you take minus 1 eigenvalue, the same expression can be written as psi minus of minus r equal to, and in right hand side you will be having minus 1, then psi minus of r, right? So this is called an odd wave function. So depending on the eigenvalues of the parity operator, we call it as even or odd wave function. For even wave function, the eigenvalue will be plus 1. For odd wave function, the eigenvalue will be minus 1. So the eigenfunctions of parity operator has definite parity. They are either even or odd. So since psi plus and psi minus are joint eigenstates of the same Hermitian operator with different eigenvalues, these states must be orthogonal to each other. That means you can write the scalar product or inner product psi plus and psi minus, the inner product between psi plus and psi minus. This is by definition, this is integral dq bar psi plus or the complex conjugate of the first quantity, then psi minus of minus r. So this can be written as integral dq bar psi plus star of r, and then we have seen that from here psi minus of minus r is given by minus of psi minus r. So this will give us multiplied by minus of psi minus r because it's an odd function. So this is equal to minus of integral d cube r psi plus star of r psi minus of r, that is minus of psi plus psi minus, the inner product between, by definition this is minus of psi plus psi minus. So what we have on left side is the inner product between psi plus and psi minus, and what we have seen that this is same as the negative of psi plus and psi minus. So this implies that this is true only when psi plus, the inner product between psi plus and psi minus is 0. That is the only condition which can satisfy this expression. So thus these states form, what we have seen is that these states psi plus and psi minus can form a complete set. So psi plus and psi minus form a complete set, and hence any function can be written as, let's say, any function psi of r, which can be written as in terms of the psi plus and psi minus, as it forms a complete set. So we can write it as psi plus of r plus psi minus of r, and this will lead us to write the even and odd functions as psi plus of r is equal to half of psi of r plus psi of minus r, and the odd function psi minus of r can be written as psi of r minus psi of minus r. Now an operator is said to be even if it obeys the condition. Let's say we have an operator A, then when we have the parity operator acting on it by A by, if it is same as the operator itself, then A is said to be an even operator. So that is the condition for an operator to be even. Pi A pi should be same as A. And let's say we have another operator B, then if we act pi on both sides, parity operator on both sides, and if this gives you minus b, then this operator b is said to be an odd operator. So that is the definition of even and odd operators. When we act with the parity operator, if it remains same, then it is even operator, or if it is the negative of the operator, then such operators are called the odd operators. So let's consider A pi. Now for even operators, what you can write is, you can write, since a is same as pi a pi, then we have one more pi. So this is parity operator pi a, the parity operator square on right hand side. We have seen that pi square will give us 1. So this will be pi a, right? Or in other words, what we have seen is that a pi is same as pi a, or it shows you that a pi minus pi a, this is the commutation between a and the parity operator. So this is 0. So you can see that the parity operator the even operators commutes with parity operator. Even operators commutes with parity operator. Now let's consider an odd operator b. Then let's say b pi. Now by definition, this is same as minus of the parity operator b, then parity operator, then we have pi. So this is minus of the parity operator b, then the square of the parity operator, right? Now the square of the parity operator is again 1, so this is minus of the parity operator b. Or you can see that b pi plus pi b equal to 0. It shows that odd operators anti-commutes. It do not commute. Anti-commutes with parity operator. Even operators commutes with parity operator, and odd operators anti-commutes with parity operator. Now what are the consequences of this commuting even operator and parity operator? What are its consequences? The first is that if the even operator is Hermitian and none of its eigenvalues are degenerate, then the eigenvectors of this even operator must be either even or odd, which is same as the eigenvectors of the parity operator. So they have a definite parity. So if you have an even operator which is Hermitian and it has a non-degenerate eigenvalue, then this commuting, the consequences of this commuting property is that the eigenvectors of the operator which you considered must be same as that of the eigenvectors of the parity operator, because we had seen in previous semester that when two operators commute, they have common set of eigenfunctions. So in principle they have a definite parity. Now if the even operator has a degenerate spectrum, its eigenvalues need not have a definite parity. Now if the even operator that you have considered is having a degenerate spectrum, that means there are more than one eigenstates with the same eigenvalue, then its eigenvalues need not have a definite parity. It can have, but it's not always, it need not always have a definite parity. So these are the consequences of the commuting property of even functions with the parity operator. And now let's see what is the parity of position and momentum operator. Now to see the parity of the position and momentum operators, let's see what happens when the parity operator acts in position space. So we had seen that in position representation we have an operator, the position operator, which when acts on this position baskets will give the position eigenvalue times the same base ket, right? Now what happens when a parity operator acts on it? When the parity operator acts on it, you have to consider the parity operator acting on this same ket. Then by definition of the parity operator, this will give us minus of r. So this is r. Then what it gives is the inversion by the action of the parity operator. Now let's consider r. Let's say parity first acts on this r base kets, then you multiply it with this position operator. Then what you have is the position operator, then by the action of pi on this r, what you get is minus of r, right? Then what you get is minus eigenvalue, minus of r, then the same ket. So it implies parity operator pi r plus r pi is equal to 0. That is, they anti-commutes. The parity operator anti-commutes with the, the position operator anti-commutes with the parity operator. So that means the parity of position operator is odd, because for even parity it should commute. Since it is anti-commute, the parity of the position operator is odd. Similarly, for momentum operator P, you can show that the parity acting on the momentum operator P is same as minus of the momentum eigenvalue times the parity operator. So this is also having the odd parity. Okay. Now we can show that even though this position and momentum do not commute with the parity operator, the square of these operators, r square and p square, commutes with parity operator. The square of these operators commutes with the parity operator. Now suppose we have a Hamiltonian of the form, let's say H is equal to some E1 potential energy time VE1 plus P square by 2m. Then this Hamiltonian will commutes with the parity operator, because if you are having an even potential, then P square commutes with the parity operator, and in such cases H commutes with the parity operator, right? So that means there exists a simultaneous eigenstates for this Hamiltonian and the parity operator. Now we have seen that for a harmonic oscillator, the Hamiltonian is given by half m omega square x square plus p square by 2m. So this potential energy is an even function because it is x square, and we have seen that the square of the x can commute with the parity and p square can also commute with parity. That means this Hamiltonian commutes with parity. Okay. Now the Hermite polynomial have a definite parity. The parity of the Hermite polynomial is given by Hn of minus x is equal to minus 1 all raised to n Hn of x. That means the parity, it can be odd or even depending whether n is odd or even. if n is odd, the parity will be odd for this Hermite polynomial. If n is even, the parity will be an even parity for the Hermite polynomial. Now, if you remember the harmonic oscillator wave function, it basically has a Hermite polynomial multiplied by a Gaussian function, and the Gaussian is an even function. Then that means what you have is the parity of the harmonic oscillator wave function is given by pi n is equal to minus 1 all raised to n. So it depends whether the quantum number n is odd or even. If it is odd, you have an odd parity for the harmonic oscillator. So all odd numbered wave functions are having odd parity, and all even numbered wave functions or even numbered states are having even parity for the harmonic oscillator problem, because this parity basically comes from the parity of the Hermite polynomial, and the multiplication factor is always having even parity. So the parity is basically determined by this parity of the Hermite polynomial. Okay.